Welcome everyone to Chapter 2, Section 4, Rates in Real Life. So far, we have emphasized the derivative as the slope of the line tangent to the graph. That interpretation is very visual and useful when examining the graph of a function, and we will continue to use it. Derivatives, however, are used in a wide variety of fields and applications, and some of these fields use other interpretations. So the following are a few interpretations of the derivatives that are commonly used. Of course, one we're used to is the general rule. The general rule for derivatives is that the derivative is the rate of change of anything. We could have the rate of change of many, many things. It's just how some object or some thing is changing over time. So here's an example. If we say that X is in years and f of X is people, then the derivative of the function with respect to X is going to be people per year, which is the rate of change in a population. Remember, the slope is always going to be equal to the rate of change, and the slope is equal to the change in Y divided by the change in X. So that would be, well, we said f of X is people. So we would have people. And we also said that X is years. So we would have people per year. And that would be the units on my rate of change. Okay. Now we have a graphical interpretation. Again, nothing new. We've been doing this since the beginning. If I have a graph, and let's say my graph is a parabola, and I want to find the rate of change of something at that point. This is X. This is f of X. X is in, oh, we don't know. Actually, X is in nothing. X is just X. So the rate of change will be the slope of the line tangent to the curve at that point. So I'm going to try to make a line that hits just that point once. Not too bad. Right? That would be, this is the tangent. And if I could find the slope of that line, I would know the instantaneous rate of change because it's happening just at that point, instantaneous. Okay. We have another interpretation, which is a physical interpretation. And why calculus is good for us is because it's important in the physical world. Often we want to find the rate of change of something with respect to time. So we're going to talk just first about velocity. If f of X is the position of an object at time X, again, it's telling us that the X is time. It's also telling us f of X is the position. So the derivative is the velocity because, again, if I were to draw a graph, and I'm going to call this X, is time. The time they're using in this example is hours. And then we have f of X, which is position. And position is in miles. So if I drew a graph, let's call it something like this. Like, I just want to draw a parabola every time. And then I want to know the rate of change right here. Then I make a tangent line through that point. This point is x, f of x. And the slope is going to equal, just like always, the change in y over the change in x. Here our y is miles, and our x is hours. Notice miles per hour gives us velocity. Okay, so that's one use. Now let's say we take the derivative again. So now we have a graph, and our graph, so I'm just looking at the old graph. It looks like the slopes pretty much everywhere are positive. So if I were to use the velocity graph as a template for how I'm going to accelerate, well, notice I'm continuously accelerating. I don't see any negative slopes there. So what I'm going to do, and this is really just, this is not specific. This is just a general graph, okay? I can say that my acceleration, maybe it goes like this, because it's always increasing, because the graph before it is increasing. So we'll call this acceleration. And we'll say this is time in hours. We're saying this is velocity. And we saw that velocity is in miles per hour. So if I take the derivative, just like it says here, I'm going to get miles per hour, change in y, or the change in f of x, divided by hours, the change in time. And I can also, using some algebra, change it into miles per hour squared. And again, that's how we really talk about the derivative in a specific case, how we can use it in the real world. Okay, so let's look at some business and economics terms. Suppose you're producing and selling some item. The profit you make is the amount of money you take in minus the amount of money you pay to produce the item. Both of these quantities depend on how many things you make and sell. So we have a function. Here's a list of definitions of some of the terminology with their meaning in algebraic terms and in graphical terms. So cost. Cost is the money you have to spend to produce your item. And here they're talking about two different kinds of costs. There's one called fixed cost and total variable cost. And they both are how much it's going to cost you to produce the item, but one stays the same if you produce one item or a million items, and the other one changes depending on the amount of items you make. Let's really talk about this for a minute and see how they differ. So the fixed cost is the amount of money you have to spend regardless of how many items you produce. Things like rent, machinery, salaries. And here they're specifying salaries for office staff, because if you're not producing anything, you don't actually have to pay somebody to come in and not do anything. But you always have to pay office staff if you have a company. So you have to pay the fixed cost even if they don't produce anything. Now let's talk about variable cost. Variable cost is having to do with the amount of items that you make. So here they're talking about Q items. So for example, things like materials you would use, the electricity to run the machines, gasoline for delivery vans, wages of your production workers. These costs vary depending on how many items you produce. If you produce one item, you need one guy to do it. If you produce 1 million items, you just can't hire one person. You have to hire many people. So that's why it's considered variable. Okay. Then we have total cost. And of course, total cost is equal to fixed cost plus total variable cost. And then we have average cost, which is still different. Total cost divided by Q, which is the number of items we're producing. Now we have something new that we would only have in a calculus class, the marginal cost. So the marginal cost, and here we're talking about producing Q items, is the cost of producing one more. Let's say we know our total cost, and then we make one more, and we find out how much it costs to make that one more thing. That would be the marginal cost. In many cases, it's easier to approximate the difference using calculus. And we're going to do an example. And some sources define the marginal cost directly as the derivative. So the marginal cost is the derivative of the total cost. And again, it's saying that the units for the marginal cost is cost per item, which should make sense because if we were to graph it, we would have the number of items on the x-axis and how much things cost on the y or vertical axis. Okay, so we're going to do this problem right here. Basically, it says, for example 1, the table shows the total cost. So this is the total cost. What does the total cost include? The total cost is equal to the fixed cost plus the total variable cost. So for example, A, what is the fixed cost? How could I find that? Well, if I produce nothing, which is what the total variable cost comes from, then I can say when Q equals 0, which means I'm producing nothing, whatever my cost is has to be fixed cost. So fixed cost is going to equal $20,000. For B, when 200 items are made, okay, now we're at 200. What is the total variable cost? Well, I know my fixed cost now, and I know my total cost. So I can say the total cost, which is equal to $45,000, is equal to my fixed cost, which I know is $20,000, plus my total variable cost. So what I want to do is just solve for my total variable cost. And how I would do that is subtract $20,000 from each side, which would give me $25,000 is equal to my total variable cost. Now, it also asks the average variable cost. Well, it's not that hard. Remember, average is just I add up how much it costs me to make all the things I'm making, and I divide by the number of things I make. So the average variable cost is going to equal 25,000 divided by, I was able to make 200 items for that amount of money. That's $125, which is the total variable cost per item. Okay. So almost there. C, when 200 items are made, estimate the marginal cost. Well, we talked about this. The marginal cost is equal to the cost of producing one more item. So if I want to know for 200, it should be 201 minus the cost to produce 200. And I'm only producing one more, so my X is 1. But we don't know how much it costs to produce 201 items. So what we have to do is basically estimate it. How do we estimate it? Well, let's say first estimate. The first estimate, let's use 200 and 100. So the cost to produce 200 items, $45,000. Minus the cost of producing 100 items is $35,000. And the difference between the two amounts that I'm producing is 200 minus 100. Basically, we have this point here, and if we call QX, then we'd have 100, comma 35,000. Here we'd have 200, comma 45,000. And here we would have 300, since we're going to use this in a minute, comma $53,000. Oh, it looks like it goes down. Isn't that interesting? Because it's costing me $10,000 to produce to go from 100 to 200. But if I'm adding another 100, it's not costing me 10,000 more. Okay, see, very interesting. So we first have, this is basically y2 minus y1 over x2 minus x1, or we can say 10,000 divided by 100. And we'll cancel all our zeros. And this gives me $100 of cost per item. Okay, well, we have our first estimate. Let's use our second estimate is going to be, we want to know if it's going to change, which we kind of saw it did, between, so this is between 100 and 200 items. This one's going to be between 200 and 300 items. And I have two numbers, and when I take the average, I'll find probably something very close to the middle, or something very close to what it would cost to produce one more than 200 items, or the marginal cost. So I have here 300 would be $53,000 minus $45,000 divided by 300 minus 200, which is equal to 8,000 divided by 100, which is equal to $80 cost per item. Okay, so we know that the marginal cost at 200 is somewhere between 100 and 180. So let's take the average of those two. Average of the two marginal costs is equal to 100 plus 80 divided by 2, which is approximately $90 cost per item. So it's a little less than 100 and it's a little more than 80. We're going to say $90. And that would be how I would estimate the marginal cost if I didn't have data that says this is how much it costs to make one more. Demand is the functional relationship between the price, which we're going to call P, and the quantity, which we're going to call Q, that can be sold. Basically, what people would demand. Okay, that's why we call it the demand function. For example, if you sold a car for $200, you would have, the price would be $200 and you'd have a gigantic demand, right? You'd sell it out in a second. If you sold that same car for $500,000, maybe Q would be 0 because that car can't be worth $500,000, or the car probably isn't worth $500,000. So it just depends on the situation. You might think of P as a function of Q, or you could say Q is a function of P. It really depends on what you're looking for. So my revenue, very important, is the amount of money that I take in from selling my products, okay? It's going to be the price times the quantity. So let's say I am a pen store. I'll just make a little table here just to make it a little easier. So I'm going to say this is quantity sold, and this is price. So I sold 40 pens at $3 a pen. I sold 20 pens at $2 a pen. And I sold 60 pens at $1 a pen. Okay. So what's my total revenue? My total revenue is going to equal, well, I sold 40 pens at $3 each, which is equal to $120. Plus, I sold 20 pens at $2 each, which is going to be $40. And I sold 60 pens at $1 each. That's plus 60. Okay, so my total revenue is $220. That means if I came in with 0 money, I now have $220 in my cash register. If I want to know, so that would be my total revenue. If I want to know my average revenue, well, if I want to know my average revenue, I do what I would normally do to find the average. I would add up all the money, which I already did. So we have $220. And then I want to know how many pens did I sell. So I'll add up my quantity. This is 120. So my average revenue is $1.83. So the marginal revenue, abbreviated MR, at Q items, so we're selling to Q things, is the amount I will take in for selling one more item. So I'm going to do the same thing. I'm going to take my margin. I'm going to say my marginal revenue is going to equal my revenue if I sell one more minus the revenue if I sell exactly what I thought. The profit is how much that's left from my total revenue, which is how much I took in that day minus how much it cost me to produce that many things, and that's my profit. So an equation for the profit is The total revenue minus the total cost gives me the profit. And the average profit should be familiar. It's the profit per item. So the marginal profit is going to equal the profit of selling the next one minus the profit of selling exactly how many I sold, or the derivative. So here's an example graphically. And let's read what it says. First, notice how to find the fixed cost and variable cost from the graph. Okay, well, how would you find the fixed cost? The fixed cost is the y-intercept of the total cost, because, so if this is the total cost, then somewhere around there is the fixed cost. Because remember, it's when I've sold nothing. And here is items sold. Here is dollars brought in. Say I didn't produce anything, but it still cost me some amount of money. That is my fixed cost. It will never go to zero because I have to rent someplace to do my business in, and so on. We already talked about that. If I want to know my total cost, I could just take this whole thing. Basically, what this is saying is if I shifted this whole thing down, this pink graph, down this many units, so that this point touches this point, which it doesn't, but if it did, then I would have my total variable cost. So my variable cost is the thing that's making it go up and down. The graph of the total variable cost would be the same shape as the graph of the total cost. It would just be shifted down. Or we could just subtract whatever that value is from the total cost. We already did that in the example. We already know that we can find the average rate of change by finding the slope of the secant lines, AC, which is average cost, average revenue, marginal cost, marginal revenue, are all rates of change, and we can find them with slopes, right? Because we said these are all derivatives. So the average cost is the slope of the diagonal line from 0 to Q comma TC of Q. All right, that's going to be a hard one. Maybe I'll use the ruler. So from the average cost is going to be from 0, 0 to Q, TC, comma Q. Basically depends on how many things I sell. So how many things you want to sell? Let's do it here. So if I wanted to know at 6 what my average cost, I can just say it's the slope of this line. Okay, so this would be the average cost. Nope. So we're going from here, 0, 0 to cost. Well, this slope of this line would be the average cost. The average revenue would be a line similar. It would go from, let's say I pick this point. Why would I pick this point? Well, of course, because it's the same Q. And I would see here that if this was the total revenue of Q, then the slope of the line, use our ruler again, would be like that. So I can see now that I have a steeper line, which means my average cost is smaller than my average revenue, which makes sense because in that space between here and here, I'm making money. Everywhere else, I'm not. Everywhere else, I'm losing money because the cost is higher than the revenue. If I wanted to find my profit at, for example, 6, I would go up and I would say, it's the distance between these 2 points vertically. This is the total revenue of producing 6 things, and this is the total cost of producing 6 things. So I find those values, I subtract them, and I get my profit. This is the rule. The profit is maximized when the marginal revenue is equal to the marginal cost. And we're going to find out why that is at a later point, but just for now, just make the assumption that it's correct. And let's look at our last example. So I can estimate a tree's age in years by multiplying its diameter in inches by its growth factor, and it depends on what species I have. According to the Missouri Department of Conservation, the growth factor for cottonwood tree is 2. So basically, if I multiply so what I'm saying is the diameter times the growth factor is equal to age. So age would be 6 times 2, which is 12 years. That's how old my tree is, 12 years old. Okay. B. What is the units of the growth factor? Well, if I know it's that the diameter is 6 inches and I'm multiplying by 2 somethings, and I come up with years, I know this means that the growth factor is years per inch. How do I know that? Because I want to end with age, and I'm starting with inches. So I can cancel inches with inches, which gives me 12 years. Is this growth factor a derivative? It is. Why is it a derivative? It is because we have a constant rate of change. The constant rate of change is my growth factor. It's not saying the first year it grows at this rate and the second year it grows at a different rate and the third year and so on. It's always growing at the same rate. That means that we have a constant rate of change, which means that 2, we could say the slope of the line is 2, which is equal to the derivative of the whatever this function is. Hopefully that makes sense. All right, that's it. Thanks a lot, guys.